All right, thank you for joining us this morning. So I want to welcome you all to today's session on quantitative data analysis. It's 8 o'clock already. We see people have started joining in. If you know others who are meant to be here, kindly inform them that we are about to start. Once again, we are excited to have with us our speaker for today, who was with us last week and who is going to be with us who will continue with us till the end of this session. And that's the whole program for the 4 weeks we'll be having these training sessions. And for those of you who were here last week, you will agree with me that it was time well spent and that it was a really eye-opening session. I want to assure you that you are in for even much more today. So just get set, get ready, and make sure you are prepared to take in all we have for today. But before we do that, I'd just like to just reiterate that for those of us here, kindly name your devices well. I see most of us have done that, which is fine. And also, during the course of the session, if you have some questions or if you have comments, feel free to drop them in the chat box. Then we'll also be notifying you of some of our training sessions that will also next month. And we also have trainings on, and we also have a webinar coming up this month, next week, on the 21st of February, Dare to Simplify. We'll be sending some of this during the course of the session. We'll also be publicizing it so that you are aware. We have loads of programs lined up for you all, and just tune in, and we hope that you join us. Again, statistics, data, and quantitative data analysis is a whole lot. There's always a lot to talk about. There's always a lot to discuss. And so because of that, we don't want to waste much time. We want to just dive in right away and kickstart today's session. Once again, we are excited and glad to have with us our trainer, who is the Director / CEO of ICOH, the Intercountry Center for Oral Health for Africa. Let's welcome to take us in our session today, Dr. Olani Itaiwo. You're welcome, sir. Good morning.
Yeah, good morning, Mr. Thank you for the introduction. Good morning, everyone. It's my pleasure to be with us again this beautiful morning. And like Osahan said, we actually have a lot to do this morning. I will just put on my slides and we set the ball rolling. Just a minute, please. Okay. So once again, good morning. Today we'll be looking at the second part of our lecture series in quantitative data analysis. And today's topics are correlation and chi-square test. My name is Nii Taiwo. It's nice to be with us. So let's just set the ball rolling. Just like I said last week, this presentation also contains some materials that got online, and they are just included for educational purposes. I'm not claiming ownership of those materials. The credit should be due to their respective authors. For a very brief revision, last class we brought up the concept of variables. And I told us that a variable is a characteristics that can change, to which we can at least point like a numerical measure. We can assign a numerical measure to it. And we said that it's different from a constant, which does not change. A constant remains the same. Please don't forget this concept. I told us that understanding this concept, that's variable and measurement scale, is cardinal to quantitative data analysis. Everywhere you will come across it. There are two types of variable. We talked about the quantitative variable, that's the one you can quantify, the one you can measure, and it can be continuous or discrete. Remember, I told you we say something is continuous if it can assume a set of infinite numbers, especially those that have a decimal point. So any form of measurement, your height, your weight, distance, temperature, pressure, anything you can measure is a continuous variable. Discrete are also quantitative variables, but they are the ones you can count: number of people, number of eggs, number of children, number of this, number of that. They are the ones you can count. They are called discrete. On the other side, we also have the qualitative variables, and it's also into two different types. The ordinal variable, which is also called a rank variable, you can order them either by ascending order or descending order, and then the nominal variable, which is just a label, the ones you can categorize, possibly like color, like gender, those are the things you can just categorize. Those ones are variables. For the purpose of this particular class, I'm going to introduce some types of variable, which are just like some descriptions of variable. Number one is the binary variable. Binary variables are actually nominal variables, but they just have two levels of expression. Observations that occur in one of two possible states. So you'll be hearing about binary variable. What it means is it's a type of nominal variable that has two levels of expression. Like you have a question, are you happy? Yes or no. This is a binary variable because it has only two levels: alive or dead, true or false, present or absent. Another name for binary variable is dichotomous variable. I'm introducing this variable because as we continue, you start coming across such kind of variables, and there are specific the quantitative data analysis or statistics that are needed, when you have binary variables. So don't forget that. Another type of variable is what we call a dependent or outcome variable, and that is the presumed effect in a study, which is like caused by another variable. Another name for this outcome variable is response variable. Let me just give us an example here. Let's say, what is the effect of sleep on weight, on body weight? Weight here is the dependent variable, or the outcome variable, or the response variable. While sleep on this other side is the independent variable. That's the one the dependent variable depend on. It's also called a predictor variable, or explanatory variable, or treatment variable. There are many synonyms, but I would just want you to possibly try and remember this: dependent or outcome variable, independent or predictor variable. Those two should suffice for what we are talking about. So don't forget, whenever you come across analysis, sometimes even in our software, you will hear or you see places where it's talked of dependent variable, independent variable. So if you don't know which one is dependent or independent variable, you mix it up. That's why I'm bringing that concept. And in textbooks, or when you are reading about biostatistics, the independent variable is normally denoted as X, while the dependent variable is denoted as Y. Let me go over it again. What is the effect of sleep on weight? So we are looking at what sleep can do to alter weight. Weight is the dependent variable, or the outcome variable, or the response variable. While sleep is the independent variable, or the predictor variable. It's what is predicting the weight, or explanatory variable. It can also be called a treatment variable. Let's assume it was like a medication. Maybe you are using medication and you are looking at the effect on the dependent variable. So that's just to introduce to us binary variable and dependent variable with independent variable. Just an introduction. And same last week, we spoke about the measurement scales. These are just numbers used to quantify numeric variables. Or sorry, they are scales used to quantify numeric variables or values for variables. We have four types of variables. We have the quantitative, which can be continuous or discrete, and then we have the qualitative, which can be ordinal or nominal. And I told us that all these variables, we can appoint or assign numbers for them if we are doing our data entry into our spreadsheet, after which we can now start analyzing. So those numbers we are assigning at the measurement scale. And I told us there are 4 scales: the nominal, the ordinal, the interval, and the ratio scale. I told us that the nominal is the least, where the number is just a label. We can say yes is 1, no is 2. We can say yes is 3, no, it's 11. The number is just label. It doesn't have anything. So you cannot add it up to find the mean or to divide it, because it's just a label. It's just to assign something there. And then the ordinal, that is where the number has a kind of degree, either increasing or decreasing, because the ordinal scale is also called the rank scale. It's either ascending or descending. The interval scale was the one I said that it also has an ordinal value, that is, there's a gradient, either ascending or descending. But don't forget, for the interval scale, I told you it does not have an absolute zero. The zero is arbitrary. And I gave us the example of temperature, 0 degrees centigrade. 0 degrees centigrade does not mean there's no temperature. It means it's freezing. Unlike in the ratio scale, 0 is not arbitrary. 0 is absolute. 0 is real. If I said that somebody has covered 0 centimeters, he has not covered anything. He's still stationary. If you have a plate, and there was 40 gram of meat there. And then after you are done, there's 0 gram of meat. That means you have eaten everything. So the zero there is absolute. And that's the difference. And these two, this nominal and ordinal, are qualitative. This interval and ratio are quantitative. We also look at the concept of data, that is a set of values of qualitative or quantitative variables. So data also follows the categories of variables. You can have quantitative or numeric data. You can have qualitative or categorical data. And under the quantitative or numeric, it follows that same description. It can be continuous or discrete, and this can also be nominal or ordinal, just as simple as that. Data are raw facts or figures from which inferences can be made and conclusions drawn. When we process data, that is what gives you an information, because it makes it more meaningful. Remember, data is just a collection, of figures or facts. But once it is processed, it becomes meaningful. Statistics is the science of collecting the data and analyzing it using mathematical operations. Statistics is the science of data collection and analysis, and it refers to information obtained by mathematical operations on numeric data. So I told us here last week, this is an example of data. It's just a collection of numeric figures, and this is just about 6. It can be in thousands. So once you have been able to process the data to give you some information, that is to make meaning, it becomes information. You have been able to process the data to make meaning, it becomes information. For example, here, 4 individuals are in the 25 to 30 kilogram group, 2 individuals are in the 30 to 35 kilogram group. That is information. But once you apply mathematical calculations, on the data, that is when you now have statistics. For example, for those 6 data, the mean is 27.67, the median is there, the standard deviation is there. These were part of the things we looked at last week. Data analysis is the process of transforming crude data into information or statistics. It is the process of transforming crude data. So this can be said to be crude data. When you analyze it, you can either have information or you have statistics, okay? And there are 2 approaches to quantitative data analysis. I need to quickly add something here so as to grant us clarity. What we are talking about is quantitative research. Quantitative research, and that is why we are talking about quantitative data analysis. However, in quantitative data analysis, we can have qualitative and quantitative variables. These 2, we now quantify them by measurement scale. We don't have statistics in qualitative research as a whole, because the kind of information we collect in qualitative research are like texts, video, audio, observations, documents. Those ones cannot be subject to mathematical calculation. So I want you to understand the difference. All we are talking about is quantitative research. And it is under quantitative research that we can do quantitative data analysis. It's different from the qualitative research, where the kind of information you collect or gather there is far different from what we are talking about. So going back to what we are discussing, for data analysis in quantitative research, there are two approaches: the descriptive or inferential. The descriptive was what we discussed last week, and that refers to information that summarizes or organizes the basic features of an entire data set. Okay. On the other side, the inferential statistics, the information extracted from the data is used to draw conclusions or make inferences or predictions about a larger population. So you have a population from where you have taken a sample. On that sample, you do a bit of calculation to now tell us that this is most likely what will have been happening in the population from where the data was drawn and from where the sample was drawn. So it aims to generalize findings to a broader context. Today, we are going to start the concept of inferential statistics. That is where we have correlation and chi-square. We have taken care of descriptive statistics last week. So this is what I was talking about. You have a population, which can be a population of any kind of unit. From that population, you did a sample, you picked a sample, and then you have a sample. If you tell us about the sample, about the variables there, that is descriptive statistics, to tell us maybe their age, their gender, their occupation, whatever it is, on and on like that, that is descriptive statistics. Now, if you now analyze the sample for you to make inferences on what might have been happening or what is happening in the population, that is inferential statistics. You are trying to infer, to predict, to propose that this is what is happening within the population using the data you have gotten from the sample. That is inferential statistics. So in our data analysis strategy, you can either be analyzing a single variable, which is the descriptive statistics, bivariate, that's two variables, or multivariate variables. So these two are the inferential statistics. The single variable is the descriptive statistics. Okay. So for the single variable, which is what we did last week, I told us about the fact that you must know a variable. It can be continuous variable, it can be categorical variable. For the continuous variable, which is quantitative, you could do your measures of central tendency, mean, median, mode. Variation, we did variance, we did standard deviation, range, percentiles, interquartile range, and your distribution. You remember we had the normal distribution curve, and we looked at the different types: the skewness, the kurtosis. And for the plot for continuous variable, it can be histogram. We spoke about box plot, stem plot, dot plot, line chart, time series chart. All this we did last week. And on the other side, for the categorical variable, where you count or you order, we did the count and frequency. This is the table. When you have a table, okay, percentages, we didn't talk about odds, okay, but that is going to come up later. And for the plot, we did a bar chart, a pie chart, and a Pareto graph. So this was just a summary of what we did last week for descriptive statistics, which is a univariate type of analysis. Now, for today, we are going to start the bivariate analysis, because here now you are comparing, or you are having two variables you are analyzing together, either to check their association, their relationship, their correlation, their impact, and on and on. Okay. And that is the beginning of inferential statistics. In inferential statistics, it allows you, the researcher, to make decisions or inferences by interpreting data patterns. Now, inferential statistics can be classified as either estimation of parameters or hypothesis testing. Please, let me just go back to introduce a particular terminology that will help us as we continue. This is population, and this is sample B. When you measure any variable in a population, it is called parameters. If you measure a variable in a sample, it is called statistics. So just understand the difference. For example, in a population, this is mean of the population. But in a sample, this is mean of the sample. Mean in a population is a parameter. Mean in a sample is a statistics. Standard deviation in a population is a parameter. Standard deviation in a sample is a statistics. So just know the difference between that term parameter and the term statistics. And it's easy. For population, parameter, it starts with P. For sample, statistics, it starts with S. That will help you to remember. Please don't forget. So let's go back to our inferential statistics. So you have estimation of parameters and hypothesis testing as the classification of inferential statistics. Under the estimation of parameters, it can be a point estimate or interval estimate, and I will explain that as we continue now. And under hypothesis testing, you could have parametric tests or non-parametric tests, and I will also explain that briefly before we continue. I need to lay all this foundation before we start our correlation and chi-square, which will just start very soon. But you need this foundation so that you can be grounded and not confused. Estimation of parameter is a process that uses sample data to determine the unknown. So you can see you are using sample data to determine the unknown parameters of a population. So you have the sample and you want to use it to predict or to identify what might be in place in the population. And there are two types. We have the point estimation and interval estimation. The point estimation is a statistical technique that uses sample data to calculate a single best guess value, a point estimate to approximate the unknown population parameter. If you recall last week when we were talking about mean, I said that it is very useful for inferential statistics. It's one of the bullet points in our mean class. It's very useful. So when we have a mean, of a population, it can give us an idea of what the population, so if we have the mean of the sample data, it can give us an idea of what the population might look like. So that's the point estimation because it's giving us a single best value, best guess, just one. On the other side, the interval estimation is used to estimate an unknown population parameter, such as the same mean or proportion, by calculating this time around a range of possible values rather than a single point value. This range is typically referred to as confidence interval, and I'm sure you have heard about that before, is an estimation of parameters, confidence interval. For a mean, we can say the mean is maybe 45, plus or minus 3. But for confidence interval, we can say it's between 41 to 48. So both of them are point estimation of parameters. One is point, the other one is a range, interval estimation. On the other side, we have the hypothesis testing, which most of you are going to be doing, especially if you're interested in research. You can't escape that. And hypothesis testing is a statistical method used to determine if there is enough evidence in a sample data to draw conclusions about a population. You can see a sample data to draw conclusions about a parameter. So that is inferential statistics. Look at this example. Do students prefer online classes to physical classes? That's a research question. You as a researcher will now have to propose an hypothesis. Possibly there is no association between online classes or there's reduced prevalence, there's increased prevalence between online classes to physical classes, and you just frame your question in a way that you can test it. And for hypothesis testing, there are many tests that can be used to test your proposed hypothesis, including t-test, chi-square, correlation, ANOVA, regression, And the particular test you are going to use will depend on the data type. The data type here is a function of the variable type. That is why I said we cannot but understand variable. So you must know the type of variable that you are working with. It will determine the kind of test you are going to do. Okay, it also depends on the distribution. Remember, we spoke about normal distribution. It is either skewed or it is kurtosis. We spoke about that also last week. It also depends on the sample size. These are some things that we have to consider in choosing, the particular hypothesis test. So depending on the type of data distribution, our hypothesis testing can be parametric or non-parametric. Let me explain what that means. So when we say the test is parametric, that means it relies on a statistical distribution. When we say it is non-parametric, it means it does not rely on a statistical distribution. What does that mean? Remember last week we spoke about a normal distribution curve. So when you have your data, because all these are going to be used for quantitative variables. So when you have your data and you plot your histogram and with your frequency plot curve, and it shows a normal distribution, that's for your continuous variable, that means that this kind of analysis will apply. You can do a parametric analysis on the data that has a normal distribution curve. However, let's assume that this is your histogram, and you can see that there's a skew. This one is a left skew. It's no longer a normal histogram distribution curve like this one. When you plot and you have something that is skewed, or there's a kurtosis, which is very significant, then you cannot use, the parametric test for that kind of analysis. You have to use a non-parametric test for your analysis. So in literal terms, parametric tests assume that your data follows a known pattern, usually a normal distribution curve. The non-parametric makes no such assumptions. Okay, so parametric tests are primarily used for quantitative continuous variables. So you can see why we must understand our measurement scale. You use them for interval or ratio scale data. The non-parametric are used for nominal or ordinal level data, or ordinal level of measurement. You can see how it comes to play now. Our measurement scale, we have the nominal, the ordinal, the interval, and then the ratio. So you must know the kind of numbers you have assigned to your variables. Once you know that your numbers are ordinal or nominal, then a non-parametric statistics is what will come into play. But if your measurement scale is interval or ratio, then you can use a parametric test, because by assumption, interval or ratio data then follow a normal distribution curve. Please don't joke with knowing what a variable is and knowing what a measurement scale is. Once you get these two, data analysis is easier. But if you just start data analysis without understanding this foundation, it becomes confusing. All right, so we are back to our data analysis strategy. And I told us that the bivariate and the multivariate is the beginning. Oh, they are the inferential statistics, but we are talking about the bivariate variables. Now, this is a chart to show us the different types of statistical tests we can do using bivariate variables. Remember, I told us that X is our independent variable, our predictor variable, our explanatory variable, and Y is our dependent variable or outcome variable or response variable. So when you are seeing these variables, please don't be confused. There are three categories we have here. We can have a situation where both our independent and dependent variable are both categorical. Now you know what categorical means. It means they are both qualitative. For example, I can say, what is the influence or what is the relationship between gender and the development of a disease? Gender is a category. You are either male or female. At least that is what we have here in Nigeria. Development of a disease is either you have it plus or you don't have it minus. You can see that both of them are categorical. And can I add that both of them are binary? If you recall that introduction of the variables, both of them are binary, both of them are categorical, and they are both nominal. It's not ordinal or any other thing. They are both nominal. So that's an example of where we have categorical Y, categorical X. And when you have a situation like that, you can do a chi-square, which is part of what we are doing. You can do a Fisher's exact, which is a modification of chi-square. You can do Manze-Haskell, and then you can do a McNemal test. What I want you to know is that all these tests here are non-parametric. Why? Because their measurement scale are either nominal or ordinal. All the tests here are non-parametric. Great. Now, let's look at, I will jump here because this is where we'll be talking about next week in our class, and then I will come to this side. Here we have both our independent variable and our dependent variable as continuous. For example, I can say, what is the influence of age on your blood pressure? Age is a continuous variable. Blood pressure is a continuous variable. And then I want to look at the relationship between the two of them. That is where I will now start talking about what we call a scatter plot, a Pearson's correlation, which is what we are talking about today, a Spearman's correlation. And this Spearman's correlation is just a variant of our, what's it called? Continuous Y, continuous X. Here, you can see a small notation here that either one of the two is not normal, that is not normally distributed. So a Pearson's correlation is actually used for an ordinal variable or a rank variable, where your variable is either ascending or descending. And we are talking about it today also. So we have three categories that is on this slide here. We have A, we have B, we have C. We will be looking at A and C. Under A, we will look at the chi-square. We will not talk about this because we can't overload you with everything. These classes are dense, so it's just to bring you to an introduction, at least for a startup. Opportunities can arise where we can talk more about some other tests, and a chi-square can be used for a situation where the category is either 2 by 2 or more than 2 by 2. This is still chi-square, where you can have maybe the color, and colors can be many, and possibly maybe the types of conditions. I have some examples that will explain that anyway. And then, like I said, we will leave B for now because B is going to be our class for next week. That is where we'll talk about t-test and ANOVA. And then we'll be talking about C in this class, and that is correlation. And in correlation, you can either have a scatter plot, a Pearson's correlation, a Spearman's correlation. Simple linear regression is another type of analysis that can be done with a continuous Y and a continuous X. And simple linear regression will be coming up in our fourth class. That is regression and contingency table analysis. So we'll just talk about the ones that concerns us today, not to overload us with too much information before we get confused. Today, we are learning two tools to answer research questions. Number one is correlation for numeric variables, we can see now. Number two is categorical, that's chi-square, for categorical variables. So this one is for quantitative, this one is for qualitative. Please don't forget, once you understand those foundation, analysis is very simple, it's just like at your fingertips. Correlation. So correlation is a statistical tool that helps to measure, describe, and analyze the degree of relationship between two, let me add, quantitative variables. Okay? The correlation analysis deals with the association between two or more variables, but we are going to be limiting ourselves to two variables because it's a type of correlation that can involve more than two variables. Okay, so we say there's a relationship, or there's a correlation if one variable tends to be accompanied by a consistent and predictable change in the other variable. So if the variables vary in such a way that one movement is accompanied by the movement of the other one, these variables are called cause and effect relationship. So there's correlation if one variable is moving in one particular direction and the other one is also moving in a consistent and predictable change in direction. Causation always implies correlation, but correlation does not necessarily imply causation. When there's something, possibly hunger, when somebody is hungry and then there's dizziness, obviously one can conclude that hunger or hypoglycemia, is causing that dizziness. But dizziness on its own does not necessarily mean that it's caused by hunger. You can be slapped. Maybe you have gone to poke nose in a fight somewhere, and then somebody throws a punch at you. You can be dizzy. It doesn't mean that dizziness must always be caused by hunger. But once there's a causation, there's a correlation. But correlation does not imply causation. I will give you an example that my biostatistics professor gave me some years back. They did a study, on ladies wearing miniskirts, and they were checking the length of the miniskirts and IQ of the ladies. And they found out that, the shorter the miniskirt, the higher the IQ. The shorter the miniskirt, the higher the IQ. Now, the question is, does it mean that the length of the miniskirt is what is giving them a better IQ? No. So all I'm trying to say is that in course of your studies, as you are doing research, you might realize there's a correlation between one variable and the other. It doesn't mean that there's a causation. So correlation can just be a side finding. Please don't forget that. So the degree of relationship between one variable and the other is measured through what we call the correlational analysis. And the analysis helps us to have an idea about the degree of the correlation and the direction of the correlation. You understand the terminologies as we are going now. So the correlation analysis typically evaluates three aspects of the relationship: the direction of the relationship or the correlation, the form of the correlation, and the degree of the correlation. And we are going to take these three one by one, short and sharp now. Number one, the direction of the correlation. The direction of the correlation is measured by the sign of the correlation, either positive or negative. Cardinal, don't forget that. The direction is measured by the sign of the correlation, either positive or negative. So we say there's a positive correlation if the two variables tend to change in the same direction. That means that if variable X is going up, variable Y is going up. That's positive. Another positive is if variable X is coming down, variable Y is coming down. That's positive. A negative correlation means that the variables tend to change in opposite direction. That means if X is going up, Y is coming down. If X is coming down, Y is going up. This one is negative, while these ones here are positive. It's very easy. You won't miss it. That's what I'm talking about. Let's assume this one is X, this one is Y. Both of them are going up. X is going up, Y is going up. Y is going up, X is going up. But for negative correlation, one is going up and the other one is going down. That is negative correlation. Okay? And this is an example of how it looks. By the way, this kind of graph you are seeing here is what is called a scatter plot. Scatter plot, and you'll be seeing plenty in the course of this presentation. Imagine that black line is not there, and it's just those dots. That's a scatter plot. So a positive or direct relationship, if the points cluster around a line that runs from the lower left to the upper right, lower left to the upper right, that is a positive correlation. But if it runs from the upper left to the lower right, it's a negative correlation, as you can see from the plot. When you have a scatter plot and you can see the direction of the arrangement of the plots or the dots, it gives you an idea which one is positive, which one is negative. That is just about the direction of the correlation. The form of correlation is the next one. The most common form of a correlation is a straight line. And that one is measured by the Pearson's correlation, which is what we are going to be talking about. There can also be a non-linear relationship. So when we talk about form of a correlation, it either is linear or it is non-linear. Those are the form, and it's very straightforward. A linear correlation is said to be linear when the amount of change in one variable tends to bear a constant ratio to the amount of change in the other variable. When you plot a graph of those variables, you have a straight line. So this is an example. We have our independent variable, we have our dependent variable. When the independent is 1, dependent is 5. On and on like that until it can generate a straight line equation. But for the nonlinear, the correlation will be nonlinear if the amount of change does not bear a constant ratio to the amount of change in the other variable. And this is what I'm talking about. It's a perfect linear relationship. And if you look at it from lower left to upper right, this one is a positive, relationship, okay? And these are also linear relationships. So this is a good example of a scatter plot. Imagine this black line is not there. You just see dot everywhere. And these are linear relationships. This one and these ones are linear relationships. These other ones are not linear. You can see they are like quadratic equations. So these are non-linear or curvilinear relationships. This is the one that concerns us in our correlation analysis. The third thing to evaluate in our correlation analysis is the degree of correlation. The measure of correlation is called the correlation coefficient and is denoted by small letter r. The degree of relationship, that is the strength or consistency of the relationship, is measured by the numerical value of r. The highest value you can have is 1, which indicates a perfect relationship. And you can have 0, which shows that there is no relationship. Because of the direction of correlation, we can have a +1 and we can have a -1. Both of them being perfect, but one negative, one is positive. So the value of R ranges from -1 to +1. It can be more than 1. Okay. Now look at this example. To look at the degree of relationship, you can see that the dots here, they are not all on the same straight line, but they are clustered close to the line. And it's positive because it's from lower upward. It's positive, and the value of R here is 0.8, which shows that it's a positive one and strong. Look at this one. It's a bit diverse, but it's still positive. This one is 0.4, moderate positive correlation. Look at this one. All the dots are perfectly aligned on a line, and that one is a 1 correlation, but it's negative because it's coming from up down. That is -1.0, perfect negative correlation. Look at this one. It's still coming from up down. That's a moderate negative correlation of 0.8. And look at this one. It's a bit more diverse and wider. This one is still negative because it's coming from up down. It's a correlation value of -0.2. Please don't forget the minus, the positive is just to denote the direction of the correlation. That means that as one is going up, the other one is going down. That is negative correlation. This one, the correlation here is 0. You can see the way the line is more like horizontal, and the thing is more like a circle. So here there is no correlation between IQ and height. You will be seeing scatter plots. That's how to interpret them, and it's a way of assessing correlation. And look at A. A is a perfect negative, perfect negative of 1. B is more like 0. If you look at it, there's no correlation. C is maybe positive or moderate positive. And D, I can say very weak negative, because the way it's looking as if the circle is tilted from up down. So this is how you will see scatter plots, and you should be able to interpret them when you see them. Now, this is an example of a scatter plot. We have 14 students here, A to N, and we are trying to look at the correlation between the family income of the children and their average grade, maybe in an exam. For example, student A, the family earns about $31,000 annually, for example, and he has an average score of 72, down to student N, where the parent earn 174,000 per annum, and the guy or the girl scored 95 as average in her score. We have plotted now a scatter plot, plotting the average grade with the family income. The grade and the income are both continuous, and that is why we can use a scatter plot. And looking at the way the dots are arranged, if you try to put like a circle around about them, from the way the circle looks, it already denotes positive. That means that the more the income, the better the score. That's all I'm trying to talk about. It's positive. However, we do know the particular value of R, how strong that correlation is. But at least from the scatter plot, you can see a kind of arrangement that is positive. The more the income, the better the score. Now, the value of R, like I said earlier on, if it is 0, that means there's no correlation. If it is 0.2, now this 0.2 can either be positive or negative. It means a very weak correlation. 0.4 to 0.4, weak correlation. 0.4 to 0.6, moderately strong correlation. 0.6 to 0.8, strong correlation. 0.8 to less than 1, very strong correlation. And if you have 1 on the dot, perfect correlation. So we can have no correlation, we can have perfect correlation. Remember, I said it cannot be greater, than 1. It's either from -1 to +1. That is how to interpret the value of R, and we'll talk about that as we continue. So how do we study correlation as a whole? There are 3 methods. Scatter diagram method, which I have been discussing previously, but I'll just make it more formal now. Number 2 is the Pearson's correlation. Number 3 is the Spearman's rank. That is the giveaway for terminology. Spearman's rank correlation. This to denote that your measurement scale, is going to be ordinal from the word rank. Okay. So for the scatter diagram, I've said it here. You just plot a graph where each point represents the value of the independent variable and the dependent variable as coordinates, just like the example of the income and the school grade that we saw earlier on. So it portrays the relationship between the two variables graphically. That's all it does for a scatter diagram. Here I have each of some children. I have the systolic blood pressure. Here I have the weight of some children, and then I have their age. Both of them are continuous variables, so we can plot a scatter diagram or a scatter plot. So let's assume this is A and this is B. The next slide shows the systolic blood pressure and the age. So to show that, as you can see, this, if we put our circle around it, is a strong correlation. As you can see, the circle is narrower. That means that as the age is increasing, the blood pressure increases. That's just a simple interpretation. As the age is increasing, the blood pressure increases. So this is a correlation analysis, but using the scatter graph. However, we don't know the particular value of R. But from here, it is obviously positive because it's going from down up. It's obviously positive. Look at this second one here. We have the scatter plot of the weight of children and their age. And if you look at the graph, it's looking distorted. That brings me back to what we discussed last week about outliers. This one is looking weird because if you are talking of age, this is already more than 100 age. So that will take you back to our table and let's look at what is happening. And if you go down and you come to here, you'll see an error somewhere, 111.6. Definitely they must have pressed the key more than twice to give you 111. So this is one way to identify outliers, and this one is an input error. So last week somebody was asking about, do we remove outliers? This particular one now you correct it because it's obviously an input error. You couldn't have seen a child who was 111.6 years old. So if we correct this value, and that's why the graph is distorted, by having one at the outlier at the extreme. So let's correct this particular value and plot again. And after the correction, you can see. Now, this is the scatter plot. I cannot say if it is actually, a positive or negative by the way it's looking. However, that is a scatter plot. But a Pearson correlation will help us to actually know the value. But from here, it's looking as if it's moderately weak or even there's no correlation, whatever it is. But that is what I am seeing in front of me. Awesome. So scatter plot, like we said, it can be positive. See the way the dots are arranged. Maybe the number of hours you spend studying and your score. The more time you spend studying and your score, ideally, they should be positively correlated. Or even as a worker, the more the years of experience, your salary should also correlate, So if you have more years of experience, your salary should also, correlate with that. And when you advertise more, spend a lot of money advertising, it is expected that your sales will also increase. So that's a positive correlation. This one is most moderate positive correlation. Compare it to this. This one is a bit bigger, but it's still positive because the direction is still from lower left to upper right. This one is a perfect negative. If you put your line across it, they will all fall on a straight line. Perfect negative, okay? This one is moderate negative, it's from up down, like the price of goods. The higher the price of goods, the lower the demand. The higher the price, the lower the demand. That's a negative correlation. The higher the time spent on TikTok, the lower the time you have to sleep. That's negative. The more the price of fuel, the lower the number of times you go for road trips. You now go and enter vehicles or commercial vehicle. So those are just examples of negative correlation. This one is a weak negative. It's still giving us the semblance of up down, but it's weak negative. And this one, obviously, there's no correlation. I mean, it's evenly scattered like a perfect cycle. Examples are your shoe size has no correlation with how intelligent you are. The month you were born does not have any correlation with your academic performance in school. your color, your favorite color does not increase your income. There is no correlation, there's no agreement, there's no alignment. So these are just examples of no correlation or very weak correlation. The advantage of scatter plot is that it is non-mathematical, very simple, and actually it is the first step when you want to do a correlation analysis. The disadvantage is that you cannot know the value of R. If you recall, I was saying that we don't know the value of R. That is just the disadvantage, but it gives us an idea of the direction, of the correlation. The other method we are looking at is the Pearson's correlation, and here we can compute our correlation when we have the values of X and values of Y, which you have gotten from your questionnaire. And the correlation, this Pearson's correlation requires that the scores be numerical. So you work with interval or ratio scale of measurement. We have discussed that, and there are other measures of correlation for other kinds of scales of measurement, like the Spearman's rank correlation. So here, the Pearson's correlation measures the direction and degree of relationship. So it can give you the direction and can also give you the value of R, the degree of correlation. Pearson's R is the most common correlation coefficient. And like I told us, it is between -1 and +1. It's not more than that. There are formulas for how this can be calculated. In previous classes, I did go through those formulas and some examples of calculation, but I thought it wise that with the way we are in this age, hardly would anybody be calculating manually, you understand? And so I have like jettisoned those formulas. I will just go towards explaining what the R means, because now you have access to softwares and the software will just give you a value of R. So let us know what the R means when you do your calculation. And we'll see some sample outputs from SPSS. If you want to do like a correlation analysis, remember it's under hypothesis testing, under inferential statistics. The first step is to generate your null hypothesis. I am assuming we know what a null hypothesis is and an alternative hypothesis. So I'm working with that assumption. For example, let's work with our age and the BP that we saw earlier on. So for a null hypothesis, I would say there's no statistically significant correlation between age and blood pressure. Most of the time, the second variable is normally your Y variable, your dependent variable, while the first variable is your X variable, your independent variable, when you are arranging a hypothesis. Please don't forget. And my alternative hypothesis is saying that there is a significantly important correlation between age and blood pressure. And this can be either positive or negative. It's either the age is increasing the blood pressure or the age is decreasing the blood pressure. We don't know. So we want to test and find out. Our second step is to calculate your correlation coefficient. The third step is to check the p-value, and then you can now have a report of your finding. So let's assume that our correlation coefficient is minus 0.4, and our p-value is 0.007. From the correlation coefficient, it's obviously negative, okay? And our p-value is very significant because it is less than 0.05, which normally is our alpha level for calculation. So one can say that there is a statistically significant evidence of an inverse or negative correlation between age and blood pressure. So if we are going to interpret this in layman's terminology, we will say that as the age of our patient is increasing, their blood pressure is reducing. That is the answer to your research question you started with. As simple as that. But remember, it's just hypothetical. But ideally, in reality, age and blood pressure is a positive correlation, because as the age is increasing, blood pressure is increasing. But that is how you interpret, a finding like this. Look at this example, of correlation output from an SPSS analysis. And the two variables we have here is height and weight. So we are looking at, the relationship between height and weight. Height is our independent variable, weight is our dependent variable. And there are four boxes here, and I'm going to explain each one to you. Look at A. You will see that for Pearson correlation, it is 1. Why is it 1? because here it is correlating height with height, so it's the constant. That is why it is 1. And if you look at the n in this box A, it's 408. What that means is that we have measurements for height that is from 408, maybe participant or patient or whatever. Now let's look at B. B is comparing height and weight, and that is where we have a Pearson correlation figure of 0.513. If you look at it very well, there is no negative mark, there's no positive mark. It is assumed that if there's no mark, it is positive. So the R value there is 0.513. And if you look at this significant two-tailed 0.00, that's our p-value. Our p-value is 0.000. That shows that it's very significant. Now look at box B and box C. It's just a mirror of the same, because in box C, you are checking weight with height, which is the same thing as what we have in box B. And you can see that in box B and C, our n value, that's the number of observations, is 354. Why is it like that? Look at box D. You understand now. In box D, we have the weight measurement, for 376 patients or participants, and we have our Pearson as 1 because the constant, weight and weight. So invariably, for the height, there were 408. For the weight, there were 376. So invariably, it's only 354 that had both measurement of height and weight, and that is the one that we can correlate. I hope you understand that. For the height, there were more people with height measurement. For the weight, we also had 376. But those that had both height and weight measurements recorded is 354, and that is the n that we are seeing, on here and here. That is the n we are seeing, So our R value is 0.513, our P value is 0.000. That is how to interpret that. This is another example of an SPSS output. Sometimes you can run many values to do correlation simultaneously. This is just an hypothetical sample. I am the one that is trying to put the meaning of the variable. So variable 1 can be age, this can be age, this can be income based on my own assumption. I'm just putting it there. Variable 3 can be weight, variable 4 can be height, variable 5 can be exam scores. And likewise here too, But by the understanding of what we had in the previous slide, let's assume you run an SPSS analysis for correlation. Wherever you see 1, 1, 1, it just shows it's a constant. That means that the variable is being compared to itself. Like variable 5 here, variable 5 here. You are comparing exam score, you are going to have what's it called? 1. Okay, so let's look at an example. I will look at 2 examples. Let's compare variable 1, that is age, and variable 2, which is income. Variable 1 and variable 2 income. And that means I'm looking at this particular, result. You can see our Pearson's correlation is 0.05, which is very, very weak, because 0 is no correlation. But this 0.05 is very, very weak. You can see the p-value is 0.448, which is not significant. And you can see the number of people involved, 214. So that is how you report that. You pick the figures, and you report it. I'm still going to be comparing the variable 1 with variable 5. Variable 1 is age, variable 5 is exam score. And I'm going to be using here as my box. By the way, whatever I get here, variable 1 with variable 5 is the same thing as variable 5 with variable 1. Like I told you, it's a mirror image. This is the same thing with this. So you can just choose one of them. You don't have to be reporting all of them. But in this particular one, look at the Pearson's correlation value, R. You will see a negative sign in front, minus 0.03. It's also very weak, but it's negative. I just want to call your attention to that minus. And our p-value is far more than 0.05. You can see it here. So it's not significant, and we still have the same number of participants, 214. On and on like that. So you can be picking them one by one and checking which is which. You can check variable 3 with variable 4. Variable 3 is weight, variable 4 is height. So let me just look at an example there. Okay, so this is going to be variable 3 and variable 4. That's variable 3 and variable 4. The correlation is also weak, the p-value is not significant, and we still have the same number of participants. So that's how you check your output to look at your value. And we said that 0 is no correlation. It goes to the left, it's negative correlation. It goes to the right, it's positive correlation. You cannot have correlation more than 1. It can either be negative or positive. So what are the assumptions of Pearson's correlation? We assume that there's a linear relationship. Remember, Pearson's correlation is based on the assumption of a straight line, okay? We also assume that we don't have outliers. You could see how the outliers distorted that scatter plot. And it is expected that you are working with numeric values, quantitative variables, and we assume there's a cause and effect relationship. They are just assumptions that you need to put in mind for your study. The advantage of Pearson's correlation is that in one value R, you can have the degree, let me say 0.8, and you can have the direction, either positive or negative. That's a very good advantage of Pearson's correlation. So when you do a Pearson's correlation, you might not need to do a scatter plot. But however, if you are doing correlation analysis, it's not bad if you just run a scatter plot first before your R value. It will even give you a guide so that your R value will agree with your scatter plots. Okay? The limitations of the Pearson's coefficient, it always assumes there's a linear relationship. That's a limitation because not every time it will be linear. We could have a curvilinear relationship, but that's an assumption. And interpreting the value of R can be difficult. And the value of correlation coefficient is affected by extreme values. So when you have outliers or extreme values, it can distort it. And if we are to calculate it manually, which I removed from the slides, it can be challenging. It takes some time to calculate and calculate and calculate. Like I said, there are softwares everywhere now, even AI. Just input your values, it will generate the R value for you. So I think we should spend more time understanding what the R stands for than calculating it. Now, I'm going to introduce another concept to us, which is the fallout of the coefficient or the correlation analysis, that value R. Remember in the previous slide, we said that interpreting it is difficult. So I'm introducing what we call a coefficient of determination. So the convenient way to interpret R, that's our coefficient, correlation coefficient, is to use the square of the value of R. And once we square it, it is called the coefficient of determination. So coefficient of determination is just R squared. Okay. So let's assume we have done our correlation analysis and we got our R value to be plus 0.9. That is very strong correlation, positive. R squared will now be 0.81. That is 0.9 times 0.9. And what this means is that 81% of the variation in the dependent variable is being explained by the independent variable. I'm going to use that example we have been using before, age and blood pressure. You can see why you must understand what a dependent variable is and what an independent variable is. So let's assume that we did our correlation analysis and our R value for this relationship is 0.9. It's just a strong correlation, but it's not giving us the meaning of what that analysis is. So you need to now determine the coefficient of determination. And by virtue of that, we now have R squared equals to 0.81. What does this mean? Please listen carefully because the understanding of this concept is going to be very useful when we start talking about simple linear regressions or regressions generally. What this means is that 81%, I've converted it to percentages. 81% of your blood pressure is explained by your age. The remaining 19% could be as a result of your diet, your lifestyle, your behavior, blah, 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 blah. But 81% of what constitutes your blood pressure is determined by your age. That is the meaning of that coefficient of determination. I have some other examples here, and I'll take them one by one. Let's assume that we are checking correlation between height and weight. And let's assume we are still working with our same R squared of 81%. That means that 81% of your weight is as a result of your height. The remaining 90% can be your diet, it can be your exercise, it can be your whatever. But 81% of your weight is as a result of your height. Here too, exercise time and blood pressure. If our R squared was 0.81, that is 81% of your blood pressure is determined by the exercise you do. Other factors now account for the remaining 90%, and on like that. That is how to interpret a coefficient of determination. The time spent reading and your exam score. That means the time you spend reading will determine 1% of your performance. The other 90% could be your intelligence, it could be your ability to buy textbooks, it could be your being punctual in school, blah, blah, blah. But 81% of your exam score is determined by the number of hours you spend reading. So if you want to pass, you spend more time reading because it accounts for 81% of your success. The maximum value of R can also be 1. It's also 1 for obvious reason, because that means 100% will have to, the maximum value is 100%. So it's either 100% is explained by 100%. You cannot have something explaining more than 100% of what is happening. So the explained variation, that is our coefficient of determination over total variation. Total variation is 100%. Like in the previous slide, it's one that we got as what is explaining the 100%. So look at another thing that I want us to know. Suppose we have two examples or two correlation analysis. One is 0.6, another one is 0.3, both of them positive. It does not mean that the first correlation is twice as strong as the second correlation. The way to interpret those values is to compute the coefficient of determination, which is R squared. So for the first one, if our R is 0.6, our R squared is 0.36. For the second one, our R is 0.3, our R squared is 0.09. So it doesn't mean that one value is twice the other. Please don't forget that. So this implies that in the first case, 36% of the total variation is explained, whereas in the second case, 9% of the total variation is explained. Let me just use something maybe for us to work with. Let's assume this is our correlation analysis for age and blood pressure. And the second one is correlation analysis for exercise and the same blood pressure, because you can do both of them. They are all quantitative variables. So it doesn't mean that age is twice the effect of exercise. That's all we are trying to say. The way you can find out what it means is to multiply it out into our coefficient of determination. So if our R squared for age is 36, that is 36%, and our R squared for exercise is just 9%, that means that our, what's it called? Our blood pressure, 36% of our age, 36% of our blood pressure is a function of our age. 9% of our blood pressure is a function of our age. Possibly, maybe 14% of our blood pressure can be a function of our diet. Maybe another 11% of our blood pressure can be a function of our family ancestry. So that is how you look at the effect of a particular variable on the dependent variable. Please don't forget that interpretation. So it's because if you add 36 and 9 together, that's just 45. That means we still have 55% accounted by other things that we don't know. It might be diet, it might be our family ancestry, it might be our sleep pattern, it might be the kind of work we are doing. So everything together like that, when added, will eventually give us the 100%. However, we know that 36% is age, 9% is exercise. How do we report correlation? Using that example that we used earlier on of weight and height, we will say that you write our R value, the degrees of freedom, and I will tell us how we calculate degrees of freedom. Degrees of freedom is actually n minus 2 for correlation. And the n here is not this n, it's not this n. It is the n that both variables have. Okay? And then we put our p-value and the statistics. So look at the report here. There was a moderately positive. How did we arrive at moderately positive? We have a key 0.0 0.4 to 0.6 is moderate, and that's our value here, 0.5. So it's in between. And it's positive because we don't have a negative mark there. And our R value is 0.51, as you can see here. And our, what's it called? Degrees of freedom is 352, which is 354 minus 2. That's how you report a correlation. By now, you should understand what this means. You should be able to report it. And if you want to go further to show that you are an A student, you can find the correlation coefficient of this value and explain further, that maybe 25% of a person's weight is accounted by the height of that person. Then we should know that you actually know what you are talking about. So these are some things to note, which is what I just spoke about in the previous slide. When you are stating your R statistics is normally to 2 decimal points. The same thing when you are doing your p-value is normally to 2 decimal points. You don't need to provide the formula for R, which is why I removed it in this presentation. And the degrees of freedom for R is n minus 2, which I've explained also in the previous slide. Awesome. The last correlation, what's it called? Method of studying correlation is the Spearman's rank correlation coefficient. Now, when the variables are not capable of quantitative measurement, but they can be arranged in either ascending or descending order, in that situation, Pearson's correlation cannot be used. We now use the Spearman's rank correlation. That means that it is ordinal. That is ordinal measurement scale. Spearman's rank correlation. And it is used in two general situations, as you can see, when the measures between the independent variable and independent variable both consist of ranks. Please don't forget that. Once you understand that basic, you can't miss it. And it measures the consistency of direction of the relationship between the variables. In this case, the two variables must be converted to ranks. When you have the measurements, you must convert them to ranks before you work on them. The calculation of Spearman correlation requires two variables observed for each individual. The observations are rank ordered. They are rank ordered, and I will explain what that means. After the variables have been ranked, the Spearman correlation is computed by either using the Pearson formula, because after you have ranked them, you can use Pearson's formula, or you use the special formula for the Spearman rank correlation. That I think we might be able to do. Let me see how much time I have, if I can squeeze it. So this is an example, and I hope to do this in the class now for us to see what I'm talking about. Dangote PLC, that's a big company in Nigeria here, shortlisted 10 candidates for final selection interview. And they were examined in their written and oral communication skills, and they were ranked as follows. That's their scores. They were ranked as follows. It's candidate 1, 2, 3, down to candidate 10. In the rank in written communication is 8. The rank in oral communication is what? Is 7. That's for, sorry, the rank in written is 8. The rank in oral for the same candidate 1 is 10. On and on and on like that. The question is that we should find out whether there's a correlation between the written and the oral communication of the shortlisted candidates. That's the question. We want to see if there's any correlation between, their spoken English and their written English, whatever it is. Okay. So we have like a table here. Look at here. There's a formula here. This is the formula for Spearman's rank correlation. And don't let the formula be scary to you. It's something very simple. It's just 1 minus 6 summation d squared. What is the summation d squared? That is the rank in x minus rank in y, and then you square them, and then you add up everything. The n here is the number. We have 10, or what's it called, 10 students or 10 candidates. Let's see if we can do something quickly here. So this one is the rank in x. This one is the rank in y. We can do x minus y. Our d, this here is x minus y, and then we can now have d squared just by squaring it. So x minus y here, this one is minus 2, this one is 0, this one is 0, that's 2 minus 2, this one is 4, this one is minus 2, this one is 1, this one is 0, 0, this one is minus 2, this one is 1. I hope that's straightforward. It's not something difficult. It's just x minus y. So our d squared here, maybe let me pick another color. So this one is going to be 4. This one is 0, 0. This is 16. This is 4. This is 1, 0, 0, 4, 1. That's just d squared. So the idea is now to add up everything, to add up all the d value. So 4 plus 16, that is 20. 20 plus 4, 24, 25, and plus another 5, that's 30. So our summation d squared is 30. As simple as that. Remember in the formula, it says 6. So we have 6 times 30 divided by our n is 10. That's 1,000. 10 times 10 times 10 is 1,000 minus 10. So everything here, 1 minus everything here. I think it's making sense. Let me clean some parts to create some space for the calculation. So here we have 180, because this times is 180, divided by 990. We can cancel this one. That's 9 here is 2, 9 here is 11. And if we find out, what's it called? 2 divided by 11, I think 0.18. Let me see if I can quickly do that. Yeah, I think 0.18, 0.18. So 1 minus 0.18 will give us 0.82. That is the value of our R. Simply done, sharp, no story. You understand? And from what we have learned from correlation, this is positive to start with. This is strong correlation, strong positive correlation. That means that as they are good in written, they are also good in oral. The more they are written performance, the more is their oral performance. So from the classwork, we have a value of 0.82. And like in the Pearson's correlation, it cannot go beyond 1, positive or negative. 1 is complete agreement positively, and minus 1 is complete agreement negatively. When it is 0, that means there's no correlation. The same interpretation with the previous one. This is what I want you to do at your own leisure time. I just want to emphasize here, that these are the marks already given. But for your own classwork, you will need to convert this performance into ranks first, please. You need to convert them into ranks first. And I will use the performance in the test as an example. You are supposed to calculate the rank correlation to determine relationship between performance in the math test and the time they spent studying. So to convert the performance into rank, I look at which one has the highest score. This is 1, and this should be number 2. This will be number 3. I'm sure this is number 4, number 5, number 6, number 7, number 8. I have converted them to ranks. You will convert this time spent also to ranks, and then these are the numbers you will use, for your formula to, what's it called, to calculate your R and find your correlation coefficient for the Spearman's rank correlation. Sharp. So just try and do that at your leisure time. What is the limitation of this Spearman's correlation? It cannot be used, for finding out correlation in a group frequency, and you can't use it for a situation where your sample size is more than 30. Okay. And what code messages from correlation? Correlation answers one simple question: when one thing changes, does the other tend to change too? Okay. Correlation tells us that two things move together, but not why they are moving together. So correlation will just tell us that, okay, this one is correlated to that. It's not telling us why is it correlated. Two variables may be correlated because a third unseen factor is affecting both. Okay. A small correlation can be important, and a large correlation may be useless, depending on the context. Okay. And a correlation can be statistically significant, but practically meaningless. I gave you the example of the miniskirt, miniskirts and the IQ. And my professor told us that was very significant. The p-value was very, very significant, but it's practically meaningless. So you can have that as a finding in your analysis. That does not mean that it's anything to hold on to. You must look at the context of what you are doing before it makes sense to you. Quickly, we will jump to the other analysis for this class, which is chi-square. I hope If you have questions, we have been jotting them down. I try to also finish before time so that we can have some discussion. Chi-square, we are going back to our bivariate table. This is where we are talking about now, and this is where you have chi-square. And remember, I told you that this is a non-parametric, what's it called? A non-parametric analysis, statistical analysis. By the way, this is supposed to be parametric, all this correlation, apart from the Spearman. This is supposed to be parametric. Okay. So the objective for this chi-square class is to learn to identify situations where chi-square is the appropriate test for use, and how you can calculate chi-square and determine the significance of the test, and very importantly, to be able to interpret chi-square like we were able to interpret correlation, and to relate the result of your analysis to your null hypothesis. Very important. That's the whole essence of data analysis. So these are sample research questions. And if you remember in that example when I was talking about gender and disease, so I'll use this as an example. So for us, we said that we believe that we have male and female here, and disease can be presence or absence of disease. So are the observed results different from the expected one? That's a situation where a chi-square can be useful. Is there a relationship between gender and development of a disease? So gender can be group A, development of the disease can be group B. Does group A have a different outcome from group B? That's another situation where chi-square can come. Is there an association between gender and disease and the development of a disease? This particular question, we might be looking at a particular variable. So we have a group, maybe class A and class B, and we are trying to check a particular, maybe intelligence quotient. No, that will not be a category. I'm looking for a category that we can check from two classes. Class A and class B, maybe color preferences. Maybe they prefer a particular color. And you want to know if there's a difference between class A and class B in the choice of a particular color. Color is categorical. Class A and class B is categorical. Are you seeing the way it works now? So you must know the type of variable you have to be able to determine the appropriate kind of analysis that will be needed to answer your question. So why do we use chi-square? It is used for categorical data that you already know by now. The data that we analyze consists of frequencies. So in other words, the variables are measured on a nominal scale. So you don't miss that. And what we use is the Pearson's chi-square. Are you seeing a kind of similarity? The previous one was Pearson's correlation. This one is Pearson's chi-square. And the magnitude of your chi-square value reflects the amount of discrepancy. So if your chi-square value is large, it shows there's a difference. If it's very little, it shows that maybe they are similar. Okay. So the chi-square statistics, this is the formula for the chi-square statistics. It's an easy formula. That's why I'm retaining it, unlike the one for correlation. That's chi-square. And it is observed minus expected squared divided by expected, and then you find the total of all those values. That is your chi-square value. Like I said, if your chi-square is small, that means that the observed and expected are similar. If your chi-square is large, that means there's a difference, something is happening. And if you want to know the magnitude of that difference of what is happening between them, then you could do an odds ratio. We'll talk about odds ratio when we are doing contingency table analysis. Okay, so by the way, before I go forward, these observed are the values you got from your own data collection. That's what you observed. The expected can be calculated, and I will show us how that is done. And likewise, like we did for correlation, you must have your steps in testing your hypothesis for a chi-square analysis. Number one, you determine that chi-square is the most appropriate test. You now establish the level of significance that you want to use. Most of the time is 0.05. You can use 0.01, you can use 0.001. People choose the one to use, but this is conventional, as most of you will have noticed. You formulate your hypothesis, you calculate your test statistic, and that's your chi-square here. In the correlation analysis, our test statistics is R. You determine your degree of freedom, and then you compare your value of x square, chi-square with a table of critical value. That is if you are doing it manually. If you are doing it using the software, it will give you the p-value and you can see if it is significant or not. So let's go on. So number one, you determine that chi-square is appropriate. So chi-square is useful when both variables are measured on a nominal scale. That is the independent and dependent, or the predictor and outcome. Can I quickly just give us one clue here? When we say independent and dependent, or I say predictor and outcome variable. So independent and dependent, that terminology is best used if you are doing an experiment. Predictor and outcome can be used for other type of study that's not an experiment. They are the same thing, but these ones are actually best used when your study is an experiment. So I've been using them interchangeably just for our level, but I'm just bringing in that by the side so that in case you come across it and you see that it's more used in experiment, that is the preference. Okay, so number two, we want to use chi-square. It can also be used when you have interval or ratio data that has been categorized. For example, you can have maybe 90 data on age, 41, 23, up to 90, but you can categorize them to less than 40 as group A, 40 or greater than 40 as group B. Now you have categorized your ratio data into categories, and by categorizing them now, they have become a nominal variable. Please don't forget that. So you can categorize, continuous variable into categories, and once you categorize them, they have become nominal variables, or it can be ordinal. At that level now, you can use a chi-square. So chi-square does not make any assumption about the distribution, and that means that chi-square is a non-parametric statistic because it doesn't make an assumption about the distribution of the shape. Okay, so you establish your p-value. Like I told us, you can choose anyone, but this is the one that is most commonly used. So we are going to be using 0.05 as our p-value. Now you are the one that will generate your hypothesis. And like I told us, we are using gender and disease. So I can say here it says the two variables are independent, null hypothesis. So I will say there is no relationship between gender and development of disease. Independent, no relationship. My alternative will say that there is an association or there is a relationship between the gender of the people and the development of a disease. So you are the one that will generate your hypothesis, and then I've just said that you have your null hypothesis. There is no statistically significant difference between A and B, and your alternative hypothesis, there is a statistically significant difference between A and B, and I used gender and development of a disease. So for gender, we have a category male and female. Development of disease is either the disease is present or the disease is absent. So those are the categories that we have, okay? Now you now calculate our chi-square. You contrast the observed frequency in each cell of a contingency table with expected frequency. The expected frequency represents the number of cases that would have been found in each cell if your null hypothesis was true. And the expected frequency is calculated by a very simple formula. That is the row frequency times the column frequency divided by the total number. Don't worry, you understand this. Don't let it confuse you. But that's the formula. So let's look at our test statistics. Chi-square is observed minus expected squared divided by expected. This is the same thing with this one. So in case you see the formula using FE or O and E, it's the same thing. Observed frequency minus expected frequency squared divided by expected frequency. So that's what I've just said. The FO is the observed frequency, the FE is the expected frequency. And you add up all of them to find out your chi-square. We are going to have a small class example. The degree of freedom for a chi-square is the number of row minus 1 and the number of column minus 1. Normally in your chi-square, if you are doing it manually, you have them in contingency tables. So you are the one that will calculate the number of the degree of freedom rather. So you now compare your value after you have calculated your chi-square. You compare it with a critical table. There's a chi-square table where you check your own value and check the value in the table. You compare the two. Now, if your own value is greater than the value in the table, then you reject your null hypothesis and then you work with your alternative hypothesis. As simple as that. If your value you calculated is greater than the value in the table, you reject your own null hypothesis, then you work with the alternative hypothesis, and vice versa. If your own value is less than the value in the critical table, then you fail to reject the null hypothesis and you work with the null hypothesis because that is the answer to your research question. This is an example of the critical table for a chi-square distribution, critical values for a chi-square distribution. We'll use it in an example that I'm going to do now. This is the column for degree of freedom, and this is the column for the p-value that you might choose to work with. So let's just continue. This is an example. Suppose you, as a researcher, you are interested in examining the relationship between heart disease, okay, and COVID-19 infection. You gave your questionnaire to 90 elderly people, and you are collecting information about their heart disease. Either there's heart disease present or absent. That's categorical, okay? And then you are checking for COVID-19 infection. It is either they are negative, they are indeterminate, or they are positive. So this is 3 categories, and your heart disease is 2 categories. Both of them are qualitative. Okay, beautiful. And by virtue of that, we can use a chi-square to check the relationship. Now, this is an example of a contingency table, and we have put in our values there. Remember, you had 90, participants. And out of the 90 participants, those that had heart disease are 50. Those that did not have heart disease are 40. Now, this is the area of the COVID-19. Out of those that had heart disease, 10 of them were negative for COVID-19, 10 were indeterminate, not sure, 30 were positive. Likewise, for those without heart disease, 15 were negative, 15 were indeterminate, 10 were positive. So we have 25 here, we have 25 here, we have 40 as those who were positive for COVID-19. This is a contingency table, and I just want you to understand it. Now, here we have our row column. Here we have our here we have our row, here we have our column, and that's the frequency of what we have for the COVID-19. This is for the heart disease. COVID-19, heart disease. This is the total of our participants. Okay. The shaded areas are the observed frequencies, which are the ones that you observed on the field from your questionnaire. Those are the ones you observed, that there were 10 people that had heart disease and they were negative for COVID-19. 10 people had heart disease, they were not sure for the COVID-19. 30 people had heart disease and were positive for COVID-19. In total, there were 50 people that had heart disease. On and on like that. These are your own observations. That's the row frequency, that is the column frequency, like I said earlier on, and this is the total of all the participants. Our first step in our hypothesis testing is to determine what is the test that we can use, the statistics. And we've seen that heart disease has 2 levels, this nominal, that's category. COVID has 3 levels, which is still nominal, is a category. So we have these two as 2 categories, and chi-square will be ideal. We establish our level of significance. An alpha level of 0.5 or 0.05 is conventional. So we are going to be working with 0.05. Then we generate our hypothesis. Our null hypothesis says that there is no relationship between heart disease and COVID-19 infection among elderly patients. Our alternative says there is a relationship between heart disease and COVID-19 infection among elderly patients. And these are the kind of hypotheses you generate for your own studies also. And like we said, this is our findings from our own study. The section in blue here, that is the observed, the ones that we found. Remember, our chi-square analysis is the summation of our observed minus expected square divided by expected. The summation covers all of them. You understand? So the next thing for us to do is to calculate our expected frequency. Our FO is observed. Our expected frequency is 13.9. This is cell 1, 2, 3, 4, 5, 6. So the question is, how did we get our expected frequency? I told us of a formula earlier on, which is our row frequency times column frequency divided by the total. So for cell 1, our row frequency is 50. 50 times column frequency, I'm talking of cell 1, that was 25, divided by n. Our n is 90. That is what gave us 13.9. Let me use the example of row cell 6. For how do we get this? Our row frequency is 40. 40 times our column frequency is 40 divided by 90. That's how we got 17.8. Let me use maybe cell 2 as another example. Our row frequency here is 50. 50 times 25, because our column frequency is 25 also, divided by 90. That's why the figure here is the same as the figure here. That's all I've just done in the previous slide. For cell 1, 50 times 25 divided by 90. For cell 4, 40 times 25 divided by 90. So that's how we got our expected frequency for each of the cells. And that's what we have there. Okay. So our, what's it called? Our chi-square test now is our observed minus expected squared divided by expected. So let's just look at this example and go back to the previous slide. Our observed is 10. 10 minus 13.9 squared divided by 30.9. That is what this is going to, that's what this is talking about. That's for cell 1, cell 2, cell 3, cell 4, cell 5, cell 6. Just observed minus expected squared divided by expected. And then once we have the value, we add up everything. That is what this sigma stands for. And our chi-square, by virtue of that, is 11.03. As simple as that. Okay. This is our observed. We want to determine the degree of freedom. And our formula for degree of freedom for chi-square is row minus 1 times column minus 1. We have two rows. 1, 2. That is why we have 2 minus 1. We have 3 columns. 1, 2, 3. That is 3 minus 1. And that's how we got 2. So our degree of freedom is 2. Row minus 1 times column minus 1. And we have said earlier on that our p-value is 0.05. Our degree of freedom is 2. So we can go and check the critical value in the table and then compare it with our own value. I think we got 0.6. Let me see. 11.03. 11.03. That's what we got from the classwork. So we want to check the table to look at the value on the chi-square table and compare with our own value that we got. On the chi-square table, like I told you, this is the degree of freedom side. Our degree of freedom is 2. And we are using a p-value of 0.05. So you are just to trace it, to look at the value that is there. So this is our critical value, 5.992. 5.992. Remember, our calculated value is 11.03. And the decision rule, like I told us earlier, is if our own calculated value is greater than the table value, then we reject the null hypothesis. Okay? Remember, if our calculated value is greater than the value in the table, we reject the null hypothesis. And this is the value on the table. This is the value we calculated. Null hypothesis is rejected. So we go with the alternative hypothesis, which says that there is a relationship between heart disease and COVID-19 infection among elderly patients. QED, that's the end of your research. You have found the answer to your study. As simple as that. It's not a difficult thing. That's a decision rule. If our own chi-square is greater than the table value, we reject the hypothesis. And so this is our answer to our study. Now, that particular example that we saw, this is it in an SPSS output. I input it in my SPSS some times back, and I generated, the output for us. This is it, Pearson's chi-square. Look at the value here. The one we calculated was 11.03. This one has just been approximated, to the nearest 2 decimal point. So It's correct. The degree of freedom from SPSS is also 2. It's correct. Now look at the p-value from SPSS, 0.004. That means that it is less than 0.05, and therefore we reject our null hypothesis, which is the same thing that we've done with the manual way. So once you have a table like this, the whole essence of this class is for you to understand this table, to understand the value of the chi-square, the degree of freedom, and the p-value, and to be able to interpret your findings in either accepting, your or rejecting your null hypothesis. As simple as that. How do you report? These are a reporting style. A chi-squared analysis showed a significant. Why is it significant? The p-value is less than 0.05. Shows a significant relationship between heart disease and COVID-19 infection among elderly patients. Our chi-square value, you put the value, degree of freedom, your p-value. That is all for a chi-square. So if somebody like me now sees this, I will be able to interpret, what your result was talking about. There is a chi-square that can be done for one-dimensional studies. It's also called a chi-square goodness of fit test. Suppose we want to know how people in a particular area, maybe in Abuja, how they will vote in this 2027 election that is coming. We have 3 major political parties, and we talk to about 60 people, and we are asking them how they will vote. 20 people are voting PDP, 30 are voting, 20 are voting APC, 30 are voting PDP, and 10 are voting Labour Party. By the way, this is just hypothetical. I'm not a politician, it's just for class example. So how will we see what's really going on? You can see that we only have one row of data. Our question is, can PDP win in Abuja? We have a null hypothesis. There is no association between how people will vote and PDP winning. Our alternative says there is an association between how people will vote and PDP winning. Now we need to do a chi-square test to determine if there is going to be a difference, from our observed and expected responses or preferences. That's our chi-square formula. But you will notice that in this particular one, we only have one rule. So the question is that how do we get our expected frequency? That's the question. And we have it here. In this kind of situation, our expected frequency is just by finding the mean, of the observed proportions. So we have three groups, and if you add everything here is 60. 60 divided by 3 is 20. That's why we have 20 here for Labour, 20 for PDP, 20 here for APC. And so if this is now our expected, we can plug it into the formula. This will be 20 minus 20 squared divided by 20. This one is here, this one is here. And we can pick our p-value, which we have already said is 0.005. And what's it called? Our degree of freedom. Here we do not have a column. We just have, we don't have rows. We only have 3 columns. 1, 2, 3. Remember, if you are picking the column, you are not doing it with the expected one. This one ideally should have been inside here. So we have the degree of freedom is row minus 1, times column minus 1. And we have only column, we don't have row. So it's going to be 3 minus 1. That means our degree of freedom is 2. Okay? So we have our degree of freedom is 2. And the calculation here, after it was done, was 10. That is our square here, our chi-square here was 10. Okay? So we have our chi-square with 2 degree of freedom, and that is our own calculated value. And this is the table value. If you check the table again, you will see that it's 5.991, like we saw earlier on. And this is the decision rule. If our own value is greater than the table value, we reject null hypothesis. And the alternative hypothesis says the district will probably vote PDP. Just as simple as that. Now, I didn't do an SPSS output for this one because, so that is our degree of freedom. Our p-value, like I said, is 5.991. So this is another example, and I think after this example, we should be done. It's a class example 2, and it says that what do doctors do with their free times? We have male doctors, and we have gender. We have gender here, and what they do with their free time. And these are categories. This one is 2, this one is 4. So we have group A, they watch TV, group B, they sleep, plan strike, or play. So we are looking at the relationship between gender and what doctors do in their leisure time. And this is the observed. By now, you should know how to calculate, what's it called, the expected. So the first thing to do in calculating the expected is to have the row, the frequency of the row, and then to the frequency of the column. So you need to generate that extra, what's it called, extra cell. This one is 50, this one is 70, this one is 60, this one is 20, this one is 70, this is 100, 100. So we have 100 male, 100 female. So if we have to calculate the expected for males that watch TV, it's going to be 100 times 50 divided by 200, because the total here is 200. That's 200 doctors. So this one, we can remove this, remove this, remove this, remove this. This is 50 divided by 2. So this will be 25. And you can calculate for each of the cells. All right. So this is what I've just done there in the previous slide. And I told us it is 20. And for the example of the male here, I said this is 25. So it's straightforward. And it can be done for all the cells. So if you do for all the cells, you can see them in parentheses. Those are the expected frequency. Our degree of freedom, we have two rows, 1, 2. Our column is 4, 1, 2, 3, 4. So our degree of freedom is going to be 3. Remember, the formula is, this one is going to be 1, this is going to be 3. 1 times 3, we have 3. Okay? So, and our p-value, like I said, is conventional, is 0.05. So we go to our table. This time around, we are using degree of freedom of p, and we are going to our p-value here. So our table value is 7.815. 7.815. So we need to calculate, if we calculate our chi-square, that formula of 0 observed minus expected squared divided by expected, this is what we will get, 10.10. And our table value is 7.82. Remember our decision rule. If our own value is greater than table value, you reject the null hypothesis. So we reject the null hypothesis and go with the alternative, which says that there is a statistically significant relationship between gender and what the doctors do with their free time. And that is the answer to your research question. That is how to interpret a chi-square. So once we see that, we will now look at the frequency to be able to explain our findings very well. That means more female and more males sleep and females they plan strike. Remember, it's hypothetical. So the highest frequency is now what we hold on to explain what is really happening, amongst our doctors. So the assumption of chi-square is that we need at least about 5 expected frequency value in our cells. Most inclusion of non-occurrences. Most include responses. It must include responses. You don't have empty cells. If you want to do a chi-square, it can cause confusion, and independence. Note that the variables are independent or all related, and that is part of what we call homogeneity of variances. Don't let me bring up that much now. When we get to t-test, we'll talk about that. To help with the last two assumptions, your n equals the total number of people who responded. Your number, that's n, equals the total number of people who responded. So this is just like a summary. For the scale, the measurement scale of both variables, if both of them are nominal, you have chi-square. If they are ordinal, you have Spearman rule. If they are interval or ratio, you have Pearson's correlation. This is just a tool to summarize all we've been talking about since morning. And in summary, as the last slide, correlation and chi-square are not about mathematics. They are just about detecting patterns in real life using data. Our next class will be talking about test and analysis of variance. I'm sure you wouldn't want to miss that. Thank you so much for your time. Over to you, Osahon, for any comments, questions, and clarifications.
Thank you very much, sir, for this very brilliant and excellent delivery on correlations and chi-square. I join the participants in applauding you and clapping for this very brilliant lecture. Thank you so much, sir. You've clarified lots of things to our audience, as we can see from the comment sections. And I want to thank you so much. So before we take just a few questions we have, a quick recap of some of the things we have done. This lecture started with a brief recap on what we did last week, talking about variables, the different types of variables. Then we now started discussing about the types of statistics, the descriptive and the inferential. And then we dwelt more, we looked at the approaches to inferential statistics, which could be estimation or hypothesis testing. And we said that under estimation, it could be the point or the interval estimates, while in hypothesis testing, we could have the parametric test or the non-parametrics. And then he gave us the different ways or when we know how to use which of them. Then he also gave us a very brilliant illustration on a table or an illustrative figure on the types of tests we could use when we have continuous categorical or continuous to continuous or categorical to categorical. And so those were just some of the preliminary things we had. Then we dwelt more today on correlations and chi-square. And in correlation, we're told that correlation helps to assess degree of relationships. And they said that three major things correlation helps us to do is it helps us with getting the direction of the relationship. So whether it's positive or it's negative, it helps us also with the form of the relationship, whether it's a linear correlation or whether it's non-linear. And then it also helps us with the degree. And from there, we saw it could be from -1 to +1. So whether it's weak, whether it's strong, or whether there's no correlation at all. And then we also looked at the different ways we could study correlation using the scatter diagrams, and we saw so many examples of them. We also saw the Pearson's correlation, and then we also looked at the Spearman's correlation and how to calculate them. And we also saw examples of some outputs of these tests. And importantly, we also tried to look at the coefficient of determination in helping us interpret our correlation findings, where we're told that the R square helps us to assess what percentage of variation in our dependent variable is explained by the independent variable. And then we went through chi-square, where he also took us through when we use chi-square, where we want to find out associations, relationships between two or more nominal variables. He also gave us the formula. We did some practical calculations. And then he also gave us a short load down on the goodness of fit test, which can also be used in a one-dimensional situation. And then we did some calculations together, and then he summarized all of this for us. So at this point, we want to once again thank our trainer for this session we have had. It has been a very, very insightful one, and I know that our audience have benefited maximally from this. So while the presentation was going on, there were some questions which I'll just quickly take them. Someone asked if, I'll just take the first two together so that we can take them. So the first one, although it has been answered, but someone said, can Spearman correlation be gotten on SPSS, or is it just by calculating with formula? I think that one, the answer is quite straightforward.
It's on SPSS.
Yes, it's on SPSS. Yes, sir. Okay. Then somebody also asked, can Spearman rank analysis be used for analysis of scale variables that are not normally distributed? So that's another question someone asked.
Good, yeah, so that's good question. So it's not for skewed variable per se. It is for ordinal variable. So you must know the type of variable you have on the measurement scale. If it is ordinal, that is where Spearman comes in. If it is skewed, and it also depends on what is your research question self. You can't just do analysis. There must be a focus and a direction you are going through. So if your data is ordinal, and definitely if you have an ordinal variable, you won't have a normal distribution anyway. So if it's ordinal and then it is skewed, obviously you can end up using your Spearmans, especially if you are trying to check the correlation between two ordinal variables.
All right, thank you, sir. Then the next question here says, okay, so this person is asking, how can our statistics be both statistically and practically significant? That's number one.
Mm.
Okay, maybe we can take that if.
Yeah, so it is the context. It is the context. I am trying to bring out. Okay, let me say that if somebody is smoking and you are trying to check the correlation with the number of cigarette sticks taken and the intensity or the blood pressure, are you following me? Both of them are continuous variable. Let's even assume that your correlation coefficient is 0.2. 0.2 is obviously weak. But if that 0.2 now gives you a p-value of less than 0.05, you can see that the correlation is a bit weak, but it is significant by p-value. And there's something we call clinical significance, because no matter how small it is, since it can show significance by p-value, one needs to now enact a kind of legislation, or maybe to encourage our patients, to reduce the number of or to reduce smoking as a whole. That is where it becomes practically significant. When your p-value shows that it's significant and you can at least pick out a bit of correlation in between them. So that p-value is what makes you to have practical significance, especially in context. In context, I'm emphasizing that, because you can just carry two data sets and just be correlating them or checking association. You will get p-values that are significant, but are they contextually reasonable? Does it make sense? I give the example of miniskirt and IQ. Very significant, but contextually it doesn't make sense. So you must look at the context and then you look at the findings also. Over to you, Osano.
Thank you, sir. So the next one is a follow-up. I think you touched it a little bit, but let me just still read it. It says, how can we establish causality as against relationship or association?
Okay, so there are, how do I put it? There are study designs that are aimed to express causality. Things like cohorts, all these analytical study designs, cohort case control, and some ecological studies. Those are some studies that are designed to check for cause and even for experimental studies. So if you have a study that is originally designed to check for causality, and you do a study that now brings about a correlation, then you can say that there is a causality there. But if you are doing a cross-sectional study, and then you are trying to check for causality from the findings of the cross, it will not really give you the actual, what's it called, result that you need. So to check for causality starts from the study design ab initio. I can be doing a cross-sectional study now and be checking the use of mosquito insecticide-treated nets and development of malaria. There are figures, there are variables. I can do a correlation and then I can see a kind of significant association. But my study ab initio was not checking for causality, because that is not a design that can be used to check for causality. But if I'm doing like a kind of cohort study and insecticide-treated net and mosquito bite and development of malaria, and then I end up analyzing and I find an association, then I can make that claim, because the study from inception was designed to check for causality. I don't know if that's making some sense.
Excellent sense, sir. Excellent sense.
Good morning, ma.
Good morning, sir.
Yes, ma.
Good morning, ma. It's always a pleasure having you around. Thank you for joining, ma. Okay, so let me just take, and this is also to acknowledge our YouTube audience. I see lots of participation from there. To the point we had almost 80 or more participants live on YouTube. There's been some questions on YouTube, some of which have been answered, but I'll just take one of them, and which says, which is better to be done in a situation of non-normal distribution of a continuous data? Is it better to transform or to resort to non-parametric tests? Then let me take the last question on the Zoom platform.
Okay.
In drawing results or writing our discussion section, which should we emphasize? Is it correlation value, chi-square, p-value, degree of freedom, critical values? Which should we emphasize? So maybe if you could just take those last two questions.
Okay,
Thank you.
awesome. So I know of statisticians that will transform their data from it being from non-parametric, and they transform it to something that can now simulate a normal distribution curve. And if you ask me for my own preference, I will just go with the non-parametric variant of the particular analysis, because they are already designed for those kind of flaws. So instead of transforming my data, I might be altering some of the real values. Why not just use the analysis that have been prepared for those kind of data? They will give me a more reliable answer or result. That is my own opinion. I wouldn't know if there's a divergent opinion to that. Now, for the other question about which one is more important, it depends on what your question is. Normally, if you run an analysis, there's a format for how it is reported. The reporting standard is uniform. So it's not as if you will report a particular figure and leave the other figure. I showed us some example. It's a standard for reporting. However, when you now get your discussion, that's where you now pick out what is relevant for you to talk about. But for reporting them, it is a standard that must be adhered to if you want to remain on that in scientific writing. There is a standard for reporting results. You don't pick a particular value. You report the result in a standardized form. But in your discussion, you pick out the value you're interested in and expound or expatiate more on that value. Thank you, Osama.
Thank you very much, sir. And with that, we come to the end of the questions and the sessions. Once again, I want to thank you and appreciate you for this enlightening session. Next week, we'll be continuing this. We will have our study on t-test and ANOVA. It's another one you don't want to miss. Make sure you're here and make sure you come in early so that we can get all we need to know. Then just a quick announcement. Same next week in the afternoon, we'll be having our monthly webinar, and we're looking at the art of the one slide story. So do you want to know how to use a single slide to present a story? Make sure you register for it and join us. The title of that talk is Dare to Simplify. So that will be coming up next week by 4 p.m. And we've already given you the links. It's on the chat box, and we'll also put it on the WhatsApp platform. So once again, I want to thank you all for coming. Thank you all for engaging with this session. And I want to thank our esteemed mentors, Professor Morenike Folayo, for being with us, for joining, and for also giving us this platform to have these sessions. Dr. Kudus Lawal, thank you so much for all you do. And once again, Dr. Olani Itaiwo, thank you for giving us of your time and of your expertise for all of this we have done. Thank you so much and enjoy the
Thank
rest of your
you.
day.